Whenever we say that HDFS runs on a cluster, we don't really mean that it has exclusive rights to it. In fact, on the very same servers, you will typically see multiple daemons belonging to different parts of Hadoop ecosystem. At the very least, on every Hadoop cluster, you will have HDFS and YARNS daemons running. Thus, a typical Hadoop cluster may look something like this. First, there will be a few master nodes dedicated to running daemons that coordinate overall activities of the cluster. For example, in HDFS's case, that overall coordination is done by a name node daemon, and you can see it running on master node number 1. But you can also see other ones, all of them colored in green, running on master nodes 1 to 4. While the master nodes are extremely critical to the overall health and performance of the cluster, strictly speaking, they don't actually do any real work. They don't store blocks of information, nor do they run data processing tasks. That happens on worker nodes. And there's typically way more worker nodes in a cluster than master nodes. In our case, you can see worker nodes going from 1 to 7, each of them running daemons colored in blue. One of those daemons is HDFS's data node, and the other one is YARN's node manager. Typically, that's all that worker nodes run. Now, just for completeness sake, we also need to mention the third kind of nodes in the cluster, a utility node. Those nodes are typically not considered to be members of the cluster, but they serve as gateways into it. You won't have to worry about them until we get to Chapter 6, where we have to review Hadoop security, but you can see one of those displayed here in the upper right corner. But back to HDFS. Let's zoom in on our daemons. Now, from HDFS's perspective, a cluster consists of a name node, coordinating a whole bunch of data nodes, but also giving 3 fundamental services to every single HDFS client. The first one is metadata management. The other one is namespace management, and the third one is block management. Metadata management deals with keeping track of permissions and ownership of files and folders, and any kind of extended metadata such as block size, replication level, user quotas, or anything else that is specific to HDFS. Namespace provides a hierarchy of namespace. Basically, all of the folders are rooted at /, and you can traverse to get to files. Knowing which files and folders are where is half the battle. The other half is knowing what blocks belong to what files and where on the cluster they are stored. That is the block map. And given that a single file can be as large as few terabytes, there is lots and lots of information, even just for a block map, to keep in memory. That makes name node particularly memory hungry. So overall, HDFS deployment begins with configuring and starting a name node on a server with lots and lots of memory. Once the name node is up and running, it makes itself available on the network, and a whole bunch of data nodes initiate connections to it. This is very important to remember. Data nodes connect to name node and not the other way around. This is one of the core design principles of Hadoop. The fact that data nodes can come and go, and all it takes to expand storage capacity of the cluster is to bring a whole bunch of the new ones online. Name node doesn't really have to care, it just keeps track of what data nodes are online and what data nodes are providing storage services in form of block information. So at every given moment, there could be data nodes that are active, shown in blue here, and the ones that are inactive or down or offline. Data node number 2, shown in gray here. Name node keeps track of all of this. Its job is to keep an eye on all the data nodes that are connected to it, and it needs to know when a given data node goes down so it can reroute requests for blocks to other data nodes. So for example, even though block 1 to 3 is hosted on 3 data nodes here, data node 1, data node 2, and data node 4, the request for block 1 to 3 can only be served from data node 1 and data node 4. Name node keeps track of that. How does it do it? Well, it does it by receiving small amounts of information every so often from all of the data nodes that are active. That small amount of information is called a heartbeat. So data node 1, for example, will be sending a heartbeat basically saying, hey, I'm still here, this is my latest heartbeat. And so will data node number 4. Data node number 2, on the other hand, will not provide a heartbeat, which will make name node realize that a replication factor for block 1 to 3 went down from 3 to 2, because it can only be reached on data node 1 and data node 4. This is enough for name node to figure out that it actually needs to initiate creation of an additional copy just to keep block 1 to 3 safe above a replication level of 3. So it does so by essentially telling a data node 1, the one that's active and actually has a copy of a block 1 to 3, to replicate block 1 to 3 to data node 3. How does it do it? Well, it does it through a replication pipeline, and we will review it next when we review how a brand new file gets written to HDFS. Now, one important thing to realize is that any HDFS interaction that we've been talking so far seem like they are coming through a name node. And it seems like all of the data transfer will also go through a central point of a name node. Now, of course, this would be horrible from a performance standpoint, and it's definitely not the case. Since it is not uncommon to have hundreds of data nodes per one name node, HDFS designers were clever enough to make sure that name node gets out of the data transfer business as quickly as possible and allows clients to fetch or send data directly from or to data nodes once they get all of the information they need. Now, name node does so as soon as it coordinates all of that metadata and a client understands what data node it actually needs to talk to. So let's take an example of a client, shown here in the upper left corner, trying to write a file to HDFS. What happens is this. First, client sends a request to the name node to add a file to HDFS. Then it receives a reply with basically name node telling it, here's your lease to a file path. Then the client will keep iterating over blocks that it has, and for every block, the client will request the name node to provide a block ID and a list of destination data nodes. Once the client has that information, the name node gets out of the way completely, and the client proceeds to write directly to the first data node in the list. So here's the first block coming to data node 1, and then data node starts writing it to disk. What happens then is the replication pipeline kicks in. It's the same replication pipeline that we've already mentioned, and it basically takes care of making sure that data node number 1 writes the copy of the block to data node number 2, and then the data node number 2 writes the copy of the block to data node number 3. Because all of the replication is done by the first data node, creating a replication pipeline to the next data node on the list, nothing like that ever gets back to the name node. This is the same kind of replication that can be triggered by the name node, in case where a number of copies of the same block in the cluster becomes low, but only then. The replication strategy employed by HDFS is actually pretty sophisticated, because HDFS is designed to assume that disk systems and networks all fail at different times. As a result, HDFS is also designed to automatically and transparently handle these failures. It does so not only by automatically replicating data across different data nodes, but also taking into account the probabilities of data corruption on the data nodes where the blocks reside. So let me show you this logic for a block write that happens to land on a data node in rack 1. The first replica then goes to a data node that sits in a different rack in a cluster. This maximizes availability of block at the downside of additional network traffic. But remember, if the server goes down, it is much more likely to go down within the same rack because of the power outage or something like that. Now, once the block actually gets to rack 2, the third replica can go to a server in the same rack, minimizing the write cost, since the block doesn't have to travel over the network and we already have a copy of the block outside of the rack 2. A different block could also begin its life on rack 1, but then it could be replicated all the way to rack 3, again maximizing availability, and the third copy will be placed within the rack 3, minimizing the write cost. The idea still remains the same. Balance the time to complete a write of all the replica against the maximizing availability if the data center failures occur.